So the next test is the PBH test, which is Popov, Belbridge and Hottis test for the stabilizability. So for stabilizability, one can also reformulate in fact this is what we have defined the PBH test as an elegant restatement of the eigenvector test, that the continuous time system is stabilizable if and only if this rank condition is satisfied for all lambdas belonging to the set of complex numbers such that the real part of those lambda is greater than or equal to 0. Right? So if you recall the result for the controllability, this condition was not there while testing the rank condition. But for stabilizability, as we had seen in the eigenvector test, that we are only concerned with the eigenvalues which are on the right hand side. So again, for stabilizability, we are concerned only with the eigenvalues which are on to the right hand side. Okay. So for the discrete time system, we would have the same result, but those eigenvalues should be outside the unit circle or on the boundary of that unit circle. So the proof of this theorem is analogous to the earlier proof, that is the controllability proof, except that now we need to restrict our attention to only the unstable portion of the set of complex numbers where the eigenvalues lies. Okay, so we won't be going through the proof of this PBH test, but if we want to determine the stabilizability directly from the given AB pair, first of all we will compute the eigenvalues of the A matrix, and then only for the eigenvalues which are on the right hand side we will carry out this test. Okay. The last test is the Lyapunov test for stabilizability. It says that the system is stabilizable if and only if there is a positive definite solution P to the following Lyapunov matrix inequality. Okay, so this is in the continuous time and this is in the discrete time domain, if we are having this pair AB coming from the discrete time system, and we term this as a LMI, which is a linear matrix inequality. So let's see the quick proof for this result. So the first implication is that the LMI has a positive definite solution matrix P, which implies that the pair AB is stabilizable. So again we would be using this eigenvector test to prove this part. So there are two assumptions here, which the first one is already given here, that the LMI has a positive definite solution P. It means that that LMI holds. Okay, the second part is that there is a non-zero vector X which happens to be the eigenvector of A transpose associated with the unstable eigenvalue lambda, that is A transpose X is equal to lambda X. Okay. So forming the quadratic form of the left hand side of the Lyapunov equation, so this was we were having on the left hand side, and then using that eigenvector we form this X star, this matrix into X, which should be less than or in fact is less than X star B transpose X, and using the property of the metric the norms, I can write this as the squared norm of B transpose X. Okay, so where star we already know that it denotes the complex conjugate transpose. So see, now proceeding in a similar way what we had done for the Lyapunov test in the controllability, this right hand side part we have represented by A star A transpose X star transpose, which would be nothing but your X star and APX. Okay, and on this side, since A transpose X star would be equal to lambda star X star, similarly here we would have A transpose X is equal to lambda X, and since lambda being scalar I can take it onto the left I can commute them, which finally I would have the twice of real part of lambda into X star Px. Okay, so see this part which is pretty much important. So since P is positive definite and we know that the real part of lambda is either greater than or equal to 0, we can conclude that this twice of real part of lambda x star px would definitely be less than of squared norm, because squared norm is positive. Hmm? P is a positive definite already, so this part would be positive definite. But since uh, lambda we are having on the onto the right hand side, which is also positive, but from this inequality, this linear matrix inequality, we would have this less than part, and which would always be greater than or equal to 0. Okay? And therefore x must not belong to the kernel of B transpose. If x happens to belong to the kernel of B transpose, we would have B transpose x equal to 0, right? But it is not equal to 0. The other direction of this implication that the AB is stabilizable implies that LMI has a positive definite solution. So we already know that the pair AB is stabilizable, and if AB is stabilizable, we can decompose it into the controllable part and the uncontrollable part. And stabilizable meaning to say that all the eigenvalues are on the left hand side. So we'll go step by step. So first of all, we from the controllability of the pair AC and BC, we have this Lyapunov equation in the context of the controllability. This is one of the results where Q's where we have this BC transpose. Okay, and PC is a positive definite solution satisfying this equation. Now on the other hand, since AU is a stability matrix, so it is already assumed in this implication that the pair AB is stabilizable. So all the eigenvalues are already onto the left hand side, and AU is a stability matrix. Now using the Lyapunov stability theorem, we can write this LMI. Okay, in terms of AU and PU is a positive definite solution of this equation. So this equation we basically have written from the stability result, and this equation we have result from the controllability result with different AC, PC and AU PU pair. Okay. So now we define another matrix P bar which is given by the elements PC and row PU on the diagonals and 0 on the off diagonal. So where rho is some positive scalar variable or parameter. So let's see this part for the complete equation which is in the result in fact. Okay. So this is in the result, so we need to show that this LMI has a positive definite solution P. Okay, so let's take the left hand side of that equation and start putting those matrices what we had obtained. A bar is basically this one. If I write all these matrices explicitly, P bar we are defining this matrix P bar, and similarly B bar I can write this BC. Now simplifying them, I would have AC into PC plus PC into AC transpose minus BC into BC transpose, which is nothing but minus of QC. So here I would have QC, and I taken the minus sign outside of this matrix. Okay. So similarly, see this part, we would have A12 rho PU here, and the rest would be 0. And with a negative sign, because we have taken the negative sign outside. Another off diagonal element, we would have AU rho into P. Sorry, this one. So here we would have this would be 0, and this would be rho PU into A transpose 1 2. Okay, and seeing the last element, we would have rho is a scalar, so I can write AU PU plus PU into AU transpose which is nothing but minus QU. So I obtained this matrix, okay, with a row multiplication. Now in order to show, so see this matrix first of all is a symmetric matrix because the off diagonal elements are equal. Okay, or let's say if I take the transpose of this matrix, I would obtain in fact this equivalent. Okay, now the second part QC we have defined already is a positive definite matrix. Okay, QU which we have obtained from the uncontrollable part is a positive definite matrix. Okay, now I can choose rho U, a very small value which is already a positive, such that the diagonal elements would be positive. If it is a positive and it is symmetric, then the entire matrix would be a positive definite matrix. And this positive definite matrix can be written, which was given in the main result. Being this matrix a positive definite matrix, we would have the right hand side the negative definite. Okay. Now since this P bar is the transformed matrix of the transform system, so in order to obtain the P matrix of the original pair AB, again using this T transformation matrix I could obtain this P, and you can verify that this P matrix satisfy that linear matrix inequality which is given in the result. Okay, so this completes the proof. So additional result we have on the controllability, that so far we have so in the first week we discussed the continuous to discrete time transformation given a continuous time system. So we need to sample our system at some sampling time t to finally obtain this discrete time system. If the discrete time system is already given to us, okay, then we had studied different tests to carry out whether the system is controllable or whether the system is stabilizable. Now we had separate tests for the continuous time system also, but now here the problem is, if I use the continuous to discrete transformation given a continuous time system, so what can I comment on to its controllability? Okay, so if you recall from the first week, so we had studied two ways of doing the discretization. The first one is using the Euler method, and the second one by assuming that UK is some piecewise constant signal between this time interval. Okay, so when we assume that U is a piecewise constant given by this one, we obtain this discrete time representation where A bar and B bar we have explicitly computed using this. A bar is given by e to the power a into the sampling time, and B bar is given by m into b, where m is the this part. Okay, so now the problem here is, which we want to address, that if the pair AB is controllable, will its sampled equation, which is given after doing the C to D continuous to discrete conversion, is controllable? Okay, so we'll see the answer to this problem. In fact, this problem is quite important in designing the so-called deadbeat sample data systems in the computer control of continuous time systems. So let lambda I and lambda I bar be respectively the eigenvalues of A and A bar. So here note that this A bar, I should have written this AD, which is the discrete time matrix of the continuous time matrix. So here A bar is not the transform matrix, algebraically equivalent transform matrix. So whenever I'm speaking of this A bar in the context of controllability after sampling, this A bar is the discrete time counterpart of the continuous time matrix A. So lambda I is the eigenvalue of this, and lambda I bar is the eigenvalue of A bar. So this is the result, that suppose that the continuous time pair AB is controllable, So sufficient condition for the discretized equation with sampling time t to be controllable is that the the imaginary part of the difference of two eigenvalues lambda I and lambda j of the continuous time system is not equal to 2 pi into m by t, where m is a positive integer. Whenever the real part of the difference of two eigenvalues is 0. Okay, so for the single input case this condition is necessary as well, but for the multiple input case this condition is only a sufficient condition. Okay, so we won't be going through the proof of this result, but we'll see various implication of this result. So first of all, notice here that if the eigenvalues of the A matrix are only on the, let's say, what could be the possible cases. So this is my S plane. Now if all the eigenvalues are onto the real axis, okay, let's say we have the eigenvalues here, or if we have the eigenvalues anywhere. Okay, if we have the eigenvalues here, then it means that the system would always be controllable, right? Because there won't be any imaginary part. Okay, now this imaginary condition is for those eigenvalues which have a complex conjugate. Let's say I have one eigenvalue here and one eigenvalue here, or one eigenvalue here and another eigenvalue here, right? Because only in this and in this case we could have the difference, the real part of the difference of two eigenvalues equal to 0, right? And only in those cases we would check the imaginary part of that difference. If that imaginary part of the difference is not equal to 2 pi m by t, where t is a sampling time, then we say that the system is, the discrete time system is also controllable. Okay. So it is straightforward to verify that if the matrix A has only real eigenvalues, then the discretized equation with any sampling period t greater than 0 is always controllable, right? So let's see. We have a complex conjugate pair of the matrix A. Now if the sampling period t does not equal to any integer multiple of pi by beta, let's recall which is the imaginary part of lambda I minus lambda j, okay, should not be equal to 2 pi m by t. Now the difference here, the imaginary part, we would have twice beta from here, and this should not be equal to 2 pi m by t, which is equivalent to saying that t is not equal to pi by beta, or for m is equal to 1. Okay, so if it is not equal to the integer multiple of pi by beta, then the discretized state equation is controllable, right? But if it becomes equal to pi by beta for some integer m, then it only says that the discretized equation may not be controllable. This is because of that, this is only a sufficient condition. So if it satisfies, if the result satisfied, it means that the discrete time version is also controllable. If it does not satisfy, it does not mean that the system is not controllable. Okay, it means that the system may not be controllable or be controllable. So we can see the implication of the second point more precisely. So first of all, note that since A bar, the discrete time state matrix, is equal to e to the power A into t, where A is the continuous time matrix and t is the sample time. If lambda I is an eigenvalue of A, then lambda I bar, which is equal to e to the power lambda I into t, is an eigenvalue of A bar. Okay, so you can take this as an exercise if you have any difficulty in visualizing this, because both the matrices A and A bar are related by this one. So the lambda I, the eigenvalues, are also related in a similar way. Okay. So see, if t becomes equal to m pi by beta for some integer m, or and given these two distinct eigenvalues alpha plus j beta and alpha minus j beta of A in fact become a repeated eigenvalue either of minus e to the power alpha t or e to the power alpha t of A bar. Okay. So we can quickly visualize this. Say for example, take lambda is equal to alpha plus j beta. So the eigenvalue of the discrete time would be e to the power alpha plus j beta into the sample time. So this I can write as e to the power alpha t, sorry, it should be j, e to the power alpha t times e to the power j beta t, and t I already know is a multiple of m pi by beta, so this would become e to the power alpha t times j m pi, and this part is nothing but either it would be plus 1 or it would be minus 1. So that's why it becomes a repeated eigenvalue of the discrete time state matrix. And this will cause the discrete time equation to be uncontrollable. So the last result we have that if the continuous time system is not controllable, then its discrete state equation with any sampling period will never be controllable matrix. Right? If the system, the LTI system is controllable, then we had a test, or you could compute the sampling time also, so that if your discrete time version of the state equation becomes controllable. Now if the original pair is not controllable, then for any sampling period your discrete time version would never be controllable.